Good morning, students. This is Arun, the Assistant Professor, Department of Electricity, DBS. So, in the previous class, I discussed about voltage regulation of a transformer and maximum expression for the voltage regulation and maximum voltage regulation condition and zero voltage regulation condition. And after that, I covered testing of transformers by using open circuit test, short circuit test, and some test. And now in this class, I am going to discuss the parallel operation of transformers and the auto transformer concept. Okay, so firstly I will start with the parallel operation of the transformer. So before going to that one, firstly we have one small concept. So that is separation of hysteresis and eddy current losses. Separation of hysteresis and eddy current losses. So you know already the hysteresis loss is P sub H is equal to K sub H into F into Bm watts per meter, and eddy current loss is equal to, that is P is equal to K into F into Bt watts per meter. So here Bm is the maximum flux density and F is the frequency, and Kh and Ke is the constants of the hysteresis and eddy current losses. So for a given AC machine and a maximum flux density, okay, for a given AC machine, that is nothing but a transformer, and maximum flux density, that is Vm. So at that condition, the hysteresis loss is directly proportional to the frequency from the equation of the hysteresis loss, that is P sub H is equal to Kh into F into Bm. So from that equation, we are writing that hysteresis loss is directly proportional to the frequency, and eddy current loss is also directly proportional to the frequency. So we will write this equation as P sub H, that is the hysteresis loss is equal to A into F, and eddy current loss is equal to D into F. Okay, so where A and B are the constants. So previously we are using the proportionality, that is hysteresis loss is directly proportional to frequency and eddy current loss is directly proportional to frequency. So we will write this equation as Ph is equal to hysteresis loss is equal to A into F, and P sub C, that is the eddy current loss, is equal to D into F. So where A and B are constants. So from the above conditions, we are writing A and B are the constants. Then we are writing the total core losses. So that is P sub psi, that is equal to, so it is the combination of hysteresis loss and eddy current losses. So that is AF plus BF square. AF plus BF square. So hence, if the total core loss for a given maximum flux density, that is Bm, is known at two frequencies, the constants A and B can be calculated. Okay, so if the total core loss for a given maximum flux density at two frequencies, the constants A and B can be calculated. So that is, knowing the values of AB, so knowing the values of AB, the hysteresis loss component and eddy current loss component of the core loss can be determined. Okay, knowing the values of A and B, that is hysteresis loss is equal to AF and eddy current loss is equal to BF square. So by using that, by knowing the values of A comma B, so the hysteresis loss component and eddy current loss component of the core loss can be determined. So further on, I am taking PT by F and F curves. Okay, PT by F and F curves. So here I have shown one characteristic diagram. Okay, so this characteristic diagram is drawn between hysteresis, iron losses versus time with respect to frequency. Okay, so here we have the curve, that is so actually we are having two curves. So one is for the ideal condition. So at that time it is a straight line. I have indicated with the dotted lines, and then we have, after this one, we have one curve that is linearly increasing. Okay, so that area is called as BF1, and secondly is called as A. So from this one I am writing PA is equal to, the total core losses is equal to AF plus BF square. So here I am taking F common, so that is PA by F is equal to A plus BF. So equating F on both sides, we will write PA by F is equal to A plus BF. So from this one, the total core losses are measured at various frequencies while the other factors upon which core losses depend are maintained constant. So the total core losses are measured at various frequencies. So Pi by P, so Pi by F and F curves by using the frequencies. So the total core losses are measured at various frequencies, while the other factors upon which core losses depend are maintained constant. So here we are varying the frequencies only, but other dependencies are maintained constant in this condition. Okay. So that is the concept of separation of eddy current and hysteresis losses in a transformer. Of course, next coming to the main concept, there is a parallel operation of transformers. Okay, parallel operation of transformers. So transformer is said to be in parallel operation when its primary winding is connected to a common voltage supply. You already know this point, and the secondary winding is connected to a common load. Okay, the transformer is said to be in parallel operation when its primary winding is connected to a common voltage supply and the secondary winding is connected to a common load. So the connection diagram of the parallel operation of a transformer is shown in the diagram. So this one, okay, here I am using the two transformers. Okay, so these transformers are connected to the is connected in parallel to a supply bus, and the primary one is connected to the supply bus and the secondary one is connected to the load through a switch. Okay, so by using this, so the parallel operation of a transformer has some advantages, like it increases the efficiency of the system and makes the system more flexible and reliable. But it increases the short circuit current of the transformers. Okay, the parallel operation of the transformers is the short circuit current of the transformers. It increases the short circuit current. Okay, so next, so reasons for parallel operation. So why we are going to parallel operation? So parallel operation of a transformer is necessary because of the following reasons are given below. Those are, it is impractical and uneconomical. So it is impractical and uneconomical to have a single large transformer for heavy and large loads. So it is impractical and uneconomical to have a single large transformer for heavy and large loads. So hence it will be a wise decision to connect a number of transformers in parallel. So so for the uneconomical purpose so actually for heavy and large loads we don't use single large transformers because of this uneconomical and impractical. There is no possibility of using single large transformers for heavy loads and large loads. So at that time we have to use it will be a wise decision to connect a number of transformers in parallel. So in substations, okay, for example, in substations, the total load required may be supplied by an appropriate number of transformers of standard size. You already know this one. So in every substation we have a particular transformers, rating of transformers. So we use those transformers of standard size to deliver the total load to the consumer. So as a result, this reduces the spare capacity of the substation. Okay, as a result, this reduces the spare capacity of the substation. So at this time, if the transformers are connected in parallel, so there will be scope in future for expansion of the substation to supply a load beyond the capacity of the transformer already installed. So actually we have a particular rating of transformer, so the transformer will supply that much of power only to the consumers. But if the transformers are connected in parallel, so there will be scope in future for expansion of the substation to supply a load beyond the capacity of the transformer already installed. Okay. Next, if there will be any breakdown of transformer in a system of transformers connected in parallel, there will be no interruption of the power supply for essential services. Okay. This will be one of the reasons why we are choosing parallel operation of transformers. So if there will be any breakdown of transformers in a system of transformers connected in parallel, there will be no interruption of power supply for essential services. So if any of the transformer from the system is taken out of service for its maintenance and inspection, the continuity of the supply will not get disturbed. Okay, this is also the main reason we are choosing that why we are choosing parallel operation of transformers means If any of the transformer from the system is taken out of service, for its maintenance and inspection, the continuity of the supply will not get disturbed. So these are the reasons why we are choosing parallel operation of transformer. And next, coming to the necessary conditions for parallel operation. Okay, necessary conditions for parallel operation. So for the satisfactory parallel operation of the transformer, the two main conditions are necessary. One is that the polarities of the transformers must be the same. Okay, the polarities of the transformers must be the same. That is terminal. This positive, negative, like that. So another condition is that the turn ratio of the transformer should be equal. Okay. Another condition is that the turn ratio of the transformer should be equal. That is N1 and N2 turns are equal. So the other two desirable conditions are as follows. So mainly we are focusing on those two conditions. So apart from that, we are going to focus on another two desirable conditions. Those are the voltage at full load across the transformer, internal impedance should be equal. Okay, the voltage at full load across the transformer, internal impedance should be equal. And next, the ratio of their winding resistances to reactances. So the ratio of resistance to reactances should be equal for both the transformers. So this condition ensures that both transformers operate at the same power factor. Okay, this condition ensures that both transformers operate at the same power factor, thus sharing their active power and reactive volt amperes according to their ratings. Okay, sharing their active power and reactive volt amperes according to their ratings. So coming to the explanation of the parallel transformers and no load condition. So the parallel operation of transformers can be easily conceived on a per phase basis. Per phase. That means per phase means actual value by base value I am taking. So we have already per unit system. In the next coming semesters, we have power system analysis subjects. So in this one we have per unit concepts. So actually one chapter is for that per unit system. Okay, so the definition of the per unit system is the ratio of actual value to the base value. So here the parallel operation of transformers can be easily conceived on a per phase basis. So the figure shows, so here I will show the diagram. It shows the two transformers parallel on both sides with proper polarities but on no load. So here I am taking the two transformers. So these are two transformers, I can do 1 and 2. I am giving the numbers to those transformers 1 and 2. And we have the load, that is ZL. And we have primary and secondary windings for both the transformers, and these are connected to the primary winding is connected to the supply and the secondary winding is connected to the load through a switch. Okay, the transformer connection for parallel operation. So here the figure shows two transformers parallel on both sides with proper polarities but on no load. So here we are considering no load condition. So the primary voltages, that is V1 and V2, are obviously equal. Okay, these are from the conditions of the transformer, parallel operation transformer. So the primary voltages, that is V1 and V2, are obviously equal. And next, if the voltage ratio of the two transformers are not identical, then the secondary induced EMF, that is E1 and E2, through in phase, though in phase, will not be equal in magnitude, and the difference in V1 minus V2 will appear across the switch as so that will appear across this switch. Okay, E1 E2 we have. So this secondary EMF, that is E1 and E2 we have for each transformer. So these two, though in phase, will not be equal in magnitude, and the difference E1 minus E2 will appear across the switch. Yes. So next, when the secondaries are parallel by closing the switch, so after closing the switch, the secondaries are parallel. Okay. At that time, a circulating current appears even though the secondaries are not supplying any load. Okay, circulating current appears even though the secondaries are not supplying any load because we are considering that no load condition. Okay. So when secondaries are parallel by closing the switch, a circulating current appears even though the secondaries are not supplying any load. So the circulating current will depend upon the total leakage impedances of the two transformers. Okay, the circulating current will depend upon the total leakage impedance of the two transformers and the difference in their voltage ratios. Okay, and the difference in their voltage ratios. So only a small difference in voltage ratios can be tolerated. Okay, only a small difference in the voltage ratios can be tolerated. So this is the explanation for the parallel operation transformers at no load condition. Okay. So next coming to the concept of auto transformer, that is single phase auto transformer. Okay. So an auto transformer is a type of transformer, is a type of electrical transformer with only one winding. So here in the auto transformer we are using, so actually in the basic transformer we are having two windings, one is primary and another one is secondary. But in the auto transformer we have one. So we have only one winding. So in the name itself, the R2, that is the prefix refers to the single coil acting alone. Okay. So in Greek we will call it as that is self. So not any automatic mechanism. Okay. Next. So an auto transformer is similar to a two winding transformer. Okay. An auto transformer is similar to a two winding transformer, but varies in the way the primary and secondary windings of the transformer are interrelated. Okay, an auto transformer is similar to the two winding transformer, but varies in the way the primary and secondary windings of the transformer are interrelated. So an auto transformer has a single winding on an iron core, and a part of the winding is common to both the primary and secondary circuits. Okay, it is of mainly two types. One is step down transformer and another one is step up transformer. Okay, sorry, step down auto transformer and step up auto transformer. So I will show those two diagrams and the basic single phase auto transformer diagram also I will show. So this is the auto transformer. Okay. So in this one we have only one winding. So if you observe this one, we have only one winding. Okay. So it has primary side and secondary side. Okay. So this is called as auto transformer, and I will show the types of auto transformer, that is step up auto transformer, step down auto transformer. So these are the two auto transformers, two types of auto transformers we have, that is step down and step up auto transformer. So if you observe this diagram, we have only one winding with the number of turns. Okay. So in this one I am using a central point for this winding, for the single winding. So in this one I am taking the turns N1 and N2. So actually we have single turns only for the single winding. This is divided into N1 and N2, and we have supply voltage V1 and V2. And in the step up transformer, same conditions we are taking, but in the reverse order. So in this one we are taking N2, these are the secondary winding turns, and N1, those are the primary winding turns, and A, B, C we are taking the points, and V1, V2 are the voltages. So these are the diagrammatic representation of step down and step up transformer, auto transformers. So here we are using only single winding, but that winding is divided into different transformers. That is for step up and step down transformers, auto transformers. Okay, next. So the voltage transformation ratio K of an ideal transformer, ideal auto transformer is, so that is K is equal to V2 by V1, so that is equal to N2 by N1, that is equal to I1 by I2. So we already know this point from the basic transformer concept, that is the transformation ratio concept, that is K is equal to V2 by V1, that is equal to N2 by N1, so that is equal to I1 by I2. So this is the transformation ratio of an ideal auto transformer. And then I will show you a diagram which shows the connections of the loaded step down as well as step up transformers. Okay. So these. So here we are considering the load. So previously I shown two types of auto transformer, step down and step up. So in those diagrams we are not considering any load, but in this condition we are taking the load. Okay. So by using this, so in each case, so in this one, in the diagram, the step up and step down transformers are loaded. So connection, it gives the connections of the loaded step down and step up auto transformers. So in that case, in each case, I1 is the input current and I2 is the output or load current. So in this diagram, so we have I1 and I2. Okay. So these currents will have I1 is the input current and I2 is the output or load current. So regardless of auto transformer connection, either it is step up or step down, regardless of auto transformer connection, the current in the portion of the winding, okay, the current in the portion of the winding, so that is common to both the primary and the secondary. Is the difference between these currents, okay, regardless of auto transformer connection, either it is step up or step down. So the current in the portion of the winding that is common to both primary and secondary is the difference between these currents, okay. So this is the difference between currents I2 minus I1, and here in this one, in this step up, I1 minus I2. Okay, both the transformers are connected to the load, auto transformers are connected to the load. In this screen, we have I1 and I2 currents. Okay, so here the current is divided, that's why I am taking the difference between these two, that is I2 minus I1. Okay, in this one, I1 minus I2. Okay, so by using these things, coming to the theory of auto transformer. Okay, so in this one, the first diagram. So in this one, we have two diagrams. On the left side we have one diagram and on the right side we have one diagram. So in those two diagrams, the first diagram shows an ideal step down transformer on load. Okay, the ideal step down transformer on load, and the figure 2 that is on the right side, it will show the equivalent circuit of the transformer From this equivalent circuit we have, so from this equivalent, that is from the 2 we have, so that is, from this one we are writing V2 into, so from this one we are writing V2 into N1 minus N2. So V2 into N1 minus N2, that is equal to N2 into V1 minus V2. So from this equivalent circuit we are writing those equations. Okay. So in this one we have primary current I1 and secondary current I2, that is the load current I2. So here we are using the step down transformer. So that's why we are having N1 and N2 turns. So in this one, the difference between the current is I2 minus I1, and we have V2. And here we have the difference between turns, that is N1 minus N2, and we have difference between the voltage, that is V1 minus V2. And on the equivalent diagram also we have the same, but here I am taking the equivalent circuit of the normal transformer. Okay, so in this one, the primary winding is connected to the supply and secondary winding is connected to the load. In this one we have the same primary current I1 and secondary current I2, and we have the voltage difference, that is V1 minus V2, and currents I2 minus I1, like that. So from these things, from these diagrams, we are taking V2 into N1 minus N2 is equal to N2 into V1 minus V2. So from this one we are writing V2 N1 minus V2 N2, so that is equal to N2 V1 minus N2 V2, and from these things we are writing V2 N1 is equal to N2 V1. Okay, V2 N1 is equal to N2 V1. Okay, so also, so from these things we are writing V2 by V1 is equal to N2 by N1, so that is equal to K. So this is the transformation ratio. So V2 by V1, that is equal to N2 by N1, that is equal to K. Also, from the equivalent diagram we are writing V1 minus V2 into I1, so that is equal to I2 minus I1 into V2. Okay, V1 minus V2 into I1, that is equal to I2 minus I1 into V2. So from this one, V1 I1 minus V2 I1, that is equal to V2 I2 minus V2 I1. So you will write this equation as V1 I1, that is equal to V2 I2. So here V1 I1 is the input apparent power and V2 I2 is the output apparent power. So in the auto transformer, the V1 I1 is equal to V2 I2. That is input power is equal to output power. Okay. So here from this one we are taking V1 I1 is equal to V2 I2 means V2 by V1 is equal to I1 by I2. V2 by V1 that is equal to I1 by I2. This is the current ratio. Okay, V2 by V1 is equal to I1 by I2. So next coming to the output of the auto transformer. So previously we are taking the diagram. So since the primary and secondary windings of auto transformer are connected magnetically as well as electrically. So the primary and secondary windings of an auto transformer are connected magnetically as well as electrically. So the power from primary is transferred to the secondary as well as conductively. That means secondary inductively as well as conductively. That means inductively means transformer action as well as conductively means conducted directly from source to the load. Conducted directly from source to the load. So from this one we are writing. So already we have output apparent power that is equal to V2 I2. So apparent power transfer inductively we have one equation, and the power transfer conductively means we have another equation, that is apparent power transfer inductively means V2 into I2 minus I1. So that is equal to V2 into I2 minus KI2. So from this one we are writing V2 into I2. So here I am taking this one V2 I2 into 1 minus K, that is equal to V1 I1 into 1 minus K. From this we are writing V2 I2 into 1 minus K. So that is equal to V1 I1 into 1 minus K. So power transfer inductively is the input, that is the input power into 1 minus K. So input power into 1 minus K. So power transfer conductively is input minus input of 1 minus K. That is here I am taking common of input, that is 1 minus of 1 minus K, that is equal to K into input. Okay. K into input, that is the power transfer conductively. So power transfer conductively is the K into input, and power transfer inductively means input into 1 minus K. Okay. So up to now we discussed about the auto transformer concept, and next coming to the saving of copper in auto transformer. Saving of copper in auto transformer. So in this section I will discuss how we save the copper in auto transformer. So for that one, for the same output and voltage transformation ratio, that is K into N2 by N1, an auto transformer requires less copper than an ordinary two-winding transformer. Okay. So for the same output and voltage transformation ratio, K into N2 by N1, an auto transformer requires less copper than an ordinary two-winding transformer. So here I am showing two diagrams. So from the below, the first figure shows an ordinary two-winding transformer, whereas figure 2 shows an auto transformer having the same output and voltage transformation ratio. Okay. So from the below figures we are showing on the left side, that is ordinary two-winding transformer, and in the right side we have second diagram. So those shows auto transformer having the same output and voltage transformation ratio, that is K. Okay. Only difference is two-winding and auto transformer. So by using these things we are taking. So the length of the copper required in a winding is proportional to the number of turns, and the area of cross section of the winding wire is proportional to the current rating. Okay. So the length of the copper required in a winding is proportional to the number of turns. Okay. And the area of cross section of the winding wire, is proportional to the current rating. So therefore the volume and hence weight of the copper required in a winding is proportional to the current into turns. Okay, that is weight of copper required in a winding, that is winding into current into turns. Okay. So winding of copper required in a winding, also that is into current into turns. So next, winding transformer. So that is the weight of copper required is proportional to I1 N1 plus I2 N2. So weight of copper required in a winding is proportional to current into turns. Okay. So here weight of the copper required is proportional to I1 N1 plus I2 N2. And coming to the auto transformer, so weight of copper required in section 1 to 2, that is I1 of N1 minus N2, and weight of copper required in section 2 to 3 is proportional to I2 minus I1 into N2. So that is this one. So this is the, we have section that is 1 to 2 and 2 to 3. So for the two-phase winding, there is two winding transformer, we don't have any sections, but in the auto transformer we are dividing the single winding into different sections. Okay, from that one we are writing, so weighting of copper required in section 1 to 2 is proportional to I1 of N1 minus N2, and weight of copper required in section 2 to 3 is proportional to I2 minus I1 into N2, and total weight of copper required is proportional to I1 of N1 minus N2 plus I2 minus I1 into N2. Okay, next. So coming to the weight of copper in auto transformer, my weight of copper in ordinary transformer, so that is equal to weight of copper in auto transformer, you already know, that is I1 of N1 minus N2 plus I2 minus I1 into N2. So please take that one into here. So I1 of N1 minus N2 plus I2 minus I1 into N2. And weight of carbon ordinary transformer is I1 N1 plus I2 N2. So from this one we are writing from the numerator N1 I1 minus N2 I1 plus N2 I2 minus N2 I1. So that means here I am multiplying in the first half of the numerator with I1 and second half of the numerator with N2. So we have N1 I1 minus N2 I1 plus N2 I2 minus N2 I1 by N1 I1 plus N2 I2. So from this one I am writing N1 I1 plus N2 I2 minus 2 N2 I1. That means minus N2 I1 minus N2 I1 means minus 2 N2 I1 by N1 I1 plus N2 I2. So from this one we are writing 2 into, from this one I am writing N1 I1 by N1 I1 plus N2 I2 means 1 minus, here we have 2 N2 minus 2 N2 I1. Okay, so because N2 I2 is equal to N1 I1, so that means it is equal to 1. So that means N1 I1 plus N2 I2 means that is 1 minus 2 N2 I1 by N1 I1 plus N2 I2. Okay, that is those two are next we have 1 minus 2 N2 I1 by, so here N2 I2 is equal to N1 I1, that means so N1 I1 plus N1 I1, that is 2 N1 I1. So from this one we are writing 1 minus, after simplifying the above one we have 1 minus N2 by N1, so that is equal to 1 minus K. You know already N2 by N1 is equal to K. So substitute here, that is 1 minus N2 by N1, that is equal to 1 minus K. Okay. So coming to this one, weight of copper in auto transformer, that is W suffix A. So that is equal to 1 minus K into weight in ordinary transformer, that is W naught. Or you will write WA is equal to 1 minus K into W naught. Or saving in copper, that is equal to W naught minus WA. So that is equal to WA minus of 1 minus K W naught. So that is equal to K W naught. These equations from the previous one are saving in copper, that is equal to K into weight of copper in ordinary transformer. Okay, saving in copper is equal to K into weight of copper in ordinary transformer. Okay. So coming to the advantages of auto transformers. Okay, so an auto transformer requires less copper than a two-winding transformer of similar rating. So an auto transformer operates at a higher efficiency than a two-winding transformer of similar rating. Okay, an auto transformer operates at a higher frequency than a two-winding transformer of similar rating, and an auto transformer has better voltage regulation than a two-winding transformer of the same rating, and an auto transformer has smaller size than a two-winding transformer of the same rating, and an auto transformer requires a smaller excited current than a two-winding transformer of the same rating. So these are the advantages of auto transformers. And coming to the disadvantages of auto transformers, so there is a direct connection between the primary and secondary. So therefore the output is no longer DC isolated from the input. So second disadvantage is an auto transformer is not safe for stepping down a high voltage to a low voltage. Stepping down a high voltage to a low voltage. and the short circuit current is much larger than for the two-winding transformer of the same rating. Okay, the short circuit current is much larger than for the two-winding transformer of the same rating. So these are the disadvantages of auto transformers. So this is the diagram for this exponential short circuit. The short circuit current is much higher, larger than for a two-winding transformer of the same rating. So here we are dividing into sections, that is 1 to 2. Here we have 230 volts, and input voltage is 11,000 volts. So here we are using the secondary winding connector to the load. Okay. So an auto transformer is not safe for stepping down a high voltage to a low voltage. So next, coming to the applications of auto transformers. So auto transformers are used to compensate for voltage drops in transmission and distribution lines. Auto transformers are used to compensate for voltage drops in transmission and distribution lines. When used for this purpose, they are known as booster transformers. When used for this purpose, they are known as booster transformers, and auto transformers are used for reducing the voltage supplied to AC motors during the starting period. Auto transformers are used for reducing the voltage supplied to AC motors during the starting period, and auto transformers are used for continuously variable supply. The auto transformers are used for continuously variable supply. So these are the different applications of auto transformers. And coming to the conversion of two-winding transformers into auto transformers. So here a two-winding transformer can be converted into an auto transformer either step up or step down. Okay, here we are taking the T diagrams. Okay, so in the first diagram, I am considering a 10 kVA, 2300 by 230 volts two-winding transformer. Okay, 2300 by 230, that is 2300 for the primary side and 230 for the secondary side. So consider a 10 kVA. So the rating of the transformer is 10 kVA, and the primary voltage is 2300 volts, the secondary voltage is 230 volts. That is a two-winding transformer shown in the diagram. And if you want to convert it into auto transformer, okay, so the two-winding transformer is if you want to convert this two-winding transformer into auto transformer, the two windings of the transformer are connected in series. Okay, the two windings of the two-winding transformer are connected in series. So if you see the second diagram, so this is the series connection of the two windings of the two-winding transformer. So in this one we have the primary winding. The primary is voltage 2300, and here we have the secondary voltage, that is 2530 volts. So that means, so if you use the additive polarity as shown in the figure 2, so here we are using additive polarity, that means we get step up auto transformer. So the voltage rating of the auto transformer is now 2300 and bar 2530 volts. So that is this one. So here we are using additive polarities. So that is, so 2300 plus 2005, that means 2300 plus 230. So primary voltage is 2300 and secondary. So in the second side we are using the additive polarity, that means 2300 plus 230, that means 2530 volts. Okay, 2530 volts. Next, if we use subtractive polarity, that is shown in, so in the second diagram we are using the additive polarity, that's why we are having 2300 by 2530 volts. And next, in the third diagram we are using subtractive polarity. So that is in this diagram. So if you use the subtractive polarity to the series connection of the two-winding transformer, so in this one the primary winding, the primary voltage is 2300 and secondary voltage is 2070. That is 2300 minus 2300 minus 230. Okay, 2300 minus 230, that means 2070. So here in the third diagram we get a step down transfer, auto transformer. So that is the voltage rating of the transformer is now 2300 2070 volts. So when a two-winding transformer is converted into auto transformer, the kVA rating of the resulting transformer is greatly increased. Okay, actually we are taking 10 kVA transformer, but after converting this two-winding transformer into auto transformer, the kVA rating of the resultant auto transformer is greatly increased. So this higher rating results from the conduction connection. Okay, this higher rating results from the conduction connection. So next, coming to the comparison of auto transformer with two winding transformer. So here we are giving the difference between the auto transformer with two winding transformer, that is. So in the two winding transformer, there are two windings in the transformer for primary side and secondary side, the two winding transformer. Then coming to the auto transformer, so in the auto transformer we have only one winding in this transformer of primary side and secondary side, only one winding. So in the two winding transformer, both windings are electrically isolated. Okay, in auto transformer, winding is not electrically isolated. So and in the two winding transformer, if number of turns on secondary side is more than primary side, it acts as a step up transformer. Okay, if number of turns on secondary side is more than the primary side, it acts as a step up transformer. In auto transformer, if the windings for output have more number of turns than the input, it acts as step up transformer. So if the winding for output have more number of turns than input, it acts as step up transformer, that is step up auto transformer. And next, so in the two winding transformer, there are two separate windings for primary and secondary, but in auto transformer only one winding. So in the winding, part of the winding is common for primary and secondary. Part of the winding is common for primary and secondary. So in the two winding transformer, no movable contact between primary and secondary. No movable contact between primary and secondary in the two winding transformer. So, but in auto transformer we have movable contact. Okay, that is movable contact is exist in the auto transformer. And next, in the two winding transformer, electrical isolation between primary and secondary windings. And in the auto transformer, we don't have electrical connection between primary and secondary. So, and in the two winding transformer, comparatively it has more losses, and in the auto transformer we have lower losses. And in the two winding transformer, efficiency is less as compared to auto transformer. So in the auto transformer, we have efficiency more as compared to the two winding transformer. So in the two winding transformer, copper required is more, but in the auto transformer, copper required is less. Thus, copper is saved in the auto transformer. And in the two winding transformer, core type or cell type core construction we are having, but in the auto transformer we have spiral core construction. Okay, so in the two winding transformer, most of the general purpose transformers where fixed voltage is required, but in the auto transformer, special applications where variable voltage is required. Okay, so these are the different comparisons between various comparisons between auto transformer with two winding transformer. Okay, thank you for watching this video. So in the next class, I am going to discuss numerical problems on single phase transformers. Up now we covered all the theory part of this fourth chapter, the single phase transformers. In the next class, I am going to discuss a problematic part of this chapter. Okay, thank you.